So I'll be showing an example of comparison of proton acidity. So for the two compounds that I'll be using, or acids, are gonna be HNO2 nitrous acid, versus H2CO3 carbonic acid. Alright, so to begin this, we're gonna first draw the Lewis dot structures for each of these acids. So we'll start with nitrous acid, which valence electrons, we'll count them for H, which is 1. N has 5 valence electrons, and O, or oxygen, has 6. Since there's 2 of them, we multiply that by 2. So 6 times 2 is 12, plus 5 plus 1, that's 18. Alright, so now we can begin drawing our little structure. We can do N right here, a little O over here, and we branch out the H. And we start by adding our little atoms, or not our atoms, our electrons. And we can add some more right here. And nitrogen needs to have or follows the octet rule, I believe, if I'm not wrong. So it needs 8 electrons in its shell. So we can add another little branch here and add a lone pair to this nitrogen so it can follow the octet rule. And we can find the formal charge for this just to make sure. So let's start with the nitrogen. We can do 5 minus 1/2 of 6, and then minus 2. And that would be half of 6, 3, 5. That's 2 minus 2, that's 0. And then we can move on to the oxygens, which are essentially the same. So 6 minus 1/2 of 4 minus 4 equals 0. And hydrogen is just 1 minus 1/2 of 2 minus 0 equals 0. And that's the Lewis dot structure for this one. So now we need to find the conjugate base for the nitrous acid, and that will be NO2 minus, I believe so, yes. Okay, so then valence electrons, you do the same by counting the electrons. So we're gonna have 5 because of nitrogen, and then we're gonna have 6 times 2 because of oxygen. And since it's negatively charged, we're gonna add 1 more, and that will be the same result, 18. And now we can draw the Lewis dot structure for that one, and that one's gonna look fairly similar, except we're just gonna take out the H from up here, so it's gonna look like this instead. O and O, like that. And then we can start filling everything. We can add some right here, add the 2 lone pairs here, and fill in the rest here. And now we can look for formal charge again, which would be for nitrogen would be the same as the top, 2, 4, 6, yep, minus 2 because there's 2 lone pairs, or 1 lone pair, and that would equal 0. And now this would be the same formal charge because, as we can see up here, it's the same structure that they have. So that would be 6 minus 1/2 of 4 minus 4 equals 0. All right. So, and now for the other oxygen, that one's a little different. So 6 minus 1/2 of, where is it? 2 right there. Minus 2, 4, 6. And so since 6 minus half of 2, which is 1, that's 5, minus the 6 here, that gives us a negative charge right there. And that's basically the conjugate base. So now for carbonic acid, we're going to do the exact same thing. We're going to find valence electrons. Hope you can see this pretty clearly. All right. So VEH, we have two H's here. So we're going to multiply 1 times 2. And then we have 1 carbon, which is 4. Oxygen, we have 6 times 3. We add those up, that's 2, 4, 6. That's 6. That's 18, 24. Right? Yes. All right. Okay, so now we can draw the Lewis dot structure for carbonic acid. And that looks like this. So we got C in the middle. We branch out to the O's. And another one right here. And we branch out to the H's, to the hydrogens. And since carbon needs to follow the octet rule as well, we need it to have 8 electrons in its little shell. So we can just add another little branch to carbon. All right, and now we can fill in the electrons. And it should look something like this. All right, and now we can look for formal charge just to make sure. Formal charge of carbon is 4 minus 1/2 of 8, because there's 8 right here, 2, 4, 6, 8, minus 0 because it has no lone pairs, and half of 8 is 0. And 4 minus 4 is 0. Okay, so now we can look for oxygen. So that would be oxygen, 6 minus 1/2 of 2, 4. 4 minus 1, 2, 3, 4, because there's 2 lone pairs. 4, half of 4 is 2. 6 minus 2 is 4. 4 minus 4 is 0. All right, and now for the H's. They're the same. So H equals 1 minus 1/2 of 2. And 0 equals 0. All right, so now the conjugate base of all of this would be HCO3, because you just take out 1 H. They basically give up 1 H, and yeah. Now we can do the same thing, find the Lewis dot structure for the conjugate base of that. All right, so let's start by counting valence electrons, which would essentially be the same, which would be H1, C would be 4, oxygen would be 6 times 3, and then since it's negatively charged, we add 1. All right, and then you just add those up, and then you get 24 again, or you should get 24, yeah. All right, so now we start with the Lewis dot structure now. All right, so we start with the, C. We can do the O's, we can branch them out. All right, O, O, O. Add one of those little branches to the other O. And then since you only took out 1 H, you leave 1 H over here. All right, and now you just fill in the dots. 1, 2, 1, 2, 1, 2, 1, 2. And then this one would have 1, 2, 3, 4, 5, 6. All right, so now we can look for formal charge. All right, so for formal charge, we can look for carbon, which would be the same. It would be 4 minus 1/2 of 8 minus 0 equals 0, so that one's fine. So now we can look for the other oxygens, which would be these two right here. This one would be 6 minus 1/2. 6 minus 1/2 of 4. 6 minus 1/2 of 4 minus 4, because we have 4 or 2 lone pairs. Oops, I don't know why I wrote the little parentheses. And that would be half of 4. 6, that would be 4. that would be 4. 4 minus 4 is 0. All right. So for the next oxygen, which would be this one right here, this one is the odd one out. So you would have 6 minus 1/2 of 2, because you only have one little bond right there. And you have 3 lone pairs, so that would be 6. And that equals half of 2. That's 1 minus 5 minus 6. That's -1. So you have a little negative charge on this one right here. All right, and then for hydrogen, obviously it's just 1. Oops, I'm getting stuck, sorry. Okay, 1. All right, focus. All right, 1 minus 1/2 of 2 equals 0, because it has no lone pair, so you can leave it like that. All right, and those are the Lewis dot structures for the acids and its conjugate bases. So now we can go and compare them. Let me just draw a line here. All right, so we're gonna start with size. So when comparing size, you're gonna look at the conjugate bases right here, and you're gonna look for the negative charge, which is these two right here, this one and this one. All right, so you have oxygen versus oxygen. I mean, they're pretty much the same. You can't really say anything else about them, so you can just say they're the same. All right, so now electronegativity. We're going to look at the electronegativity of both of these and their neighboring atoms. All right, so with this, you're going to, well, let's see, electronegativity of O is going to be, and you can look at this through your periodic table, it's going to be 3.44. All right, and that's going to be for oxygen. And since they're both the same, so the electronegativity for the individual atoms right here, they won't really matter because they're the same. So now we're going to compare them to the neighboring atoms right here. So for nitrogen, for nitrous acid, the electronegativity is going to be, let me take a look. It's going to be 3.04. So that's going to be for, let me label these real quick, H or NO2 minus, and then the O for the other one would be 3.44 because it's the same, and this one would be for HCO3 minus. All right, and then for the neighboring atom, which is carbon, the electronegativity for that one would be 2.55. And so now you find the change in electronegativity between the two. So you can subtract them to find out which one is more stable. So we can do this right here. So it's 3.44 minus 3.04, and I get 0.4. 0.40, right? That's the change in electronegativity. And then for this one, we got 3.44 minus 2.55, and I get 0.89. So I got 0.89 for this one. And from this, we can tell that this one's going to be more stable. So the nitrous acid is going to be more stable and therefore making it more acidic. And well, these are just different methods to tell which one is more acidic than the other. So this is telling us that this one right here is going to be more acidic. And you can also check the resonance, which is the last method, resonance. And we're gonna go based off of the conjugate base structure. So we're gonna draw the one we drew up there. So it's gonna be like this, and fill in the dots, or electrons, I mean. So we're gonna find resonance for this Lewis dot structure, and to do that, you're basically, to find resonance, what's happening here is you're pushing one of these lone pairs to the center, and it creates a bond. And then for the other side, you push one of these, what's it called, bonds to the exterior of the atom, and it turns into electrons. And you can do this again through the instruction that the professor gave us. You can label these as 1, 2, 3, because in order to do this you need a double bond and a single bond, and this would be 1, this would be 2, this would be 3. They have to be connected, and then when that happens you get resonance, and it turns like this. It turns into this basically. So since you gave up that bond to the outside, you're left with one bond, and nitrogen is still the same, and you get 2 bonds over here, and you basically give up the lone pair here to the bond in the middle, and you're left with 2 lone pairs on this side and 3 lone pairs on this side. And the negative charge also moves to the other side. And those are the only, those 2 are the only resonance structures that this molecule has. I mean, sorry. And that would be for NO2 minus resonance structure right there. All right, and then for the other side, which would be HCO3 minus, you're gonna do the same. You're just going to move the, we're gonna draw the same structure we drew up here, which is this one right here. We're gonna draw it again to show you how it looks like. Oops, sorry, I can't see that. Okay. And then you're gonna do the other side. And then you're gonna add the last oxygen at the top. All right, so that's what the structure looks like right now. So we can't go this way because this one already has 8 electrons in its little shell, and since oxygen, I believe, abides to the octet rule, you can't touch that one basically. So for this, it's going to start from here basically. You're going to go 1, 2, 3. So again, what's happening? You're pushing one of these out, and you're making one of these go to the center. And then, let me scroll down a little, not scroll, move the paper. And then you get resonance. And then the structure looks like this. It just changes a little bit. You move this bond. Oh no, you move one of the bonds up here. So now this one has a full shell. Or not, oh yeah. And then the other one gets 2 bonds in the middle. And it has 2 lone pairs. And then this one ends up with 3 lone pairs now. And this one has a negative charge as well. And then the rest stays the same. So from this one, you can only get 2 resonance structures, because like I mentioned before, you can't mess around with this anymore because this already has a full octet here, and like this one didn't right here. So you can mess around with these 2 right here. And those are basically the 2 resonance structures you can get from the 2 molecules. And you can't really tell much from this because they both have both 2 resonance structures. But that doesn't matter, because in the second step that we did, we found out that this this molecule right here was more stable. And if it's more stable, it basically means that it's more acidic, and that was basically it for the problem. We can tell that HNO2 is more acidic. And that's it. Thank you.